Okay. All right. So welcome everyone to our sixth seminar for the spring 2021. And as becoming our tradition, we have our students, chemistry, biochemistry majors that introduce our speaker. So today, that pleasure and responsibility falls to Andrew Wee. But I will introduce Andrew, who will then introduce the speaker. So Andrew is a sophomore. He's a biochemistry major. He's from California, Redlands, California. He attended Redlands High School. He plans to get into medical school and also has some hopes also maybe of serving in the military. He's one of his favorite sports is soccer. So you guys play soccer out in Cali? I didn't know that, Andrew. Anyway, anyway, he's been playing it for 12 years. Wow. You started pretty young, Andrew.
I did.
Anyway, thanks for accepting to welcome and introduce our speaker today.
So our speaker is Dr. Sidney Malik Wilkerson Hill, and he was born in Kinston, North Carolina. He began his undergraduate study at North Carolina State University. And in 2010, he received his bachelor's degree of science in polymer and color chemistry through the College of Textiles and a bachelor's degree of science in chemistry through the College of Physical and Mathematical Sciences. After his undergraduate career, Dr. Sidney Hill researched at the UC Berkeley under Professor Richmond Sarpong. Here he researched about the transition metal catalyzed cycloisomerization reactions to access natural products scaffolds. And he has received numerous awards such as the National Science Foundation Graduate Research Fellowship and an Outstanding Graduate Student Instructor Award. Additionally, Dr. Sidney was inducted into the Phi Beta Kappa Academic Honor Society. Currently, he is an assistant professor at UNC Chapel Hill in the chemistry department, where he focuses on the total synthesis of complex natural products and heterocyclic compounds. Today, he will be talking about complex secondary metabolites, which are used for drug development, and the goal with his research is to discover new ways to come to complex dimeric natural products. Please join me in welcoming Dr. Sidney Hill.
All right. Thank you, Andrew. I appreciate that. That was a great introduction. Thank you so much. And thank you, Desmond, for the invite to Andrews. This is fantastic being here virtually. And I'm super excited to share some work that we have going on in the lab today. So what I'm going to do is just go ahead and try to share screen. Hopefully everything works again. All right, drum roll, bear with me.
Okay, let's just make sure. There you go. You should be able to share your screen.
Okay.
Yep.
There we go.
Mm-hmm.
All right. So I hope this doesn't pop up through the whole talk.
Okay.
All right. There we go. Fantastic.
All right.
Excellent. All right. So hopefully everyone can hear me okay. If you can't, just shoot a message in the chat or just raise your hand with an emoji. Okay. Again, it's a pleasure to be here today. I'm super excited to share with you some of the work that's going on down at the University of North Carolina, Chapel Hill. So for those of you who are not familiar with me or my lab, I'm a new professor down there. So we started summer of 2018. So this is year 2.5, year 3 for us. And we're getting off the ground. Okay. So today I'd like to tell you about some of the projects going on in the lab. We are really excited and interested about complex molecules isolated from nature. Okay. Now, why do we care about these? And I think the best way to sum this up is that nature has the absolute best medicine cabinet. So I'm primarily excited about complex molecules because of their ability to become medicines. All right. And it's been cited that approximately 60% of all of our medicines on the market today are inspired by natural products. Okay. So natural products are secondary metabolites that are isolated from various plants or bacteria or fungi, all right? And I have 4 molecules on the screen, some of which you may be familiar with, right? And they all help human health in some way, shape, or form. So on the far left, I have this molecule, acetylsalicylic acid, also known as aspirin, all right? And it's been used extensively for pain relief, right? Whereas this molecule, penicillin G, is known to be an antibacterial. And as you know, morphine is used for pain relief also, and also in the palliative care process, all right? Now, the molecule that kind of stands out here that you might not be familiar with is this molecule on the right called aconitine, okay? Now, this is not a molecule we're going after in our lab, but I always like to include it because it does have really interesting biological activity. So aconitine is isolated from this genus of plants called aconitum, all right? And it's actually a potent poison, but the way it works is by inhibiting sodium ion channels, all right? So it's a blocker, which means it could be used for the treatment of pain later on if we could find better ways to synthesize it. Now, if I were to ask everyone in the room which one was the most complex molecule and thus the hardest one to build, your eyes would automatically gravitate towards aconitine, right? And you know, this idea of molecular complexity is an interesting one, right? So it's kind of this idea that I think if you look at a molecule, you know which one is the most complex, but how do you actually like quantify that? And what terms do we use to describe the complexity of molecules, all right? So when we think of molecular complexity, we're thinking of the number of rings a compound has, the number of elements such as carbon, nitrogen, oxygen, sulfur, so on, whether a molecule is flat versus three-dimensional, and also how many basic heteroatoms it has, right? Such as this nitrogen here, right? So, you know, by these metrics, right, we can easily say that aconitine is the most complex molecule on the slide, all right? And it's important to consider molecular complexity because, you know, if you wanted to go out and actually build aconitine so you can study its you know, biochemical properties, then you need really good synthetic methods to do that, right? So the things you're learning in organic 1 and organic 2, like SN2 reactions and elimination reactions, those are, you know, those have stood the test of time. But arguably, when you're thinking about building more complex molecules, those tools that you're learning break down, okay? And so that's where synthetic organic chemists come in. We essentially try to develop new reactions to access complex chemical architectures that cannot be accessed by known means. All right, so on this slide, I have a potpourri of molecules that we are excited about in the Hill lab, all right, all of which have interesting medicinal properties, all right? So the reason we're interested in structurally complex molecules can be summed up in the center of the slide. Structural complexity often informs new reaction methodology. So if you need to find a way to bake some of these dimeric natural products, for example, which are shown on the slide, you should probably you would be inclined to develop a method that would be broadly applicable to all of these molecules. All right, and so today's talk is going to be a progress report, if you will, on this molecule we're developing in the lab, this linchpin reagent, as we call it. All right, so this molecule is known as bis-chlorocrylonitrile, but in our laboratory we call it biscan. Okay, I'm going to show you how we're using biscan to access some of these dimeric natural products. All right, now if you just give me a moment, what I'm going to try to do is switch to my laser pointer because I realized I didn't have that on. Okay, there we go. All right, and so these types of dimeric natural products are known as polyketide natural products, which means they fall out of this polyketide biosynthetic pathway. All right, and so for those of you taking biochemistry, you know that a polyketide is essentially an oligomer of acetyl-CoA. So for some of these dimeric natural products, acetyl-CoA, you take 10 equivalents of that, and that's oligomerized, all right, and that's bound to an acyl carrier protein, right? After loss of water and oxidation, you can get to some of these anthraquinone type monomers, which after a few more biosynthetic steps are ultimately takes you to your monomeric system, okay? So your key building blocks here are, again, acetyl-CoA and malonyl-CoA. These are the building blocks that make up some of these polyketide natural products, right? Now, when you're thinking about how the dimers arise, it's a little bit of a black box, all right? So these dimers, right, can arise from their monomeric units through a variety of methods, right? So Sometimes a cytochrome P450 enzyme, so something that is an oxidant, will facilitate an oxidation event, which builds the key CC bond in those dimers. Sometimes it's a flavin-dependent monooxygenase, all right? So this is just kind of a fancy way of saying a transition metal-free oxidation, if you will, all right, to forge this key CC bond. Sometimes these monomers dimerize spontaneously, all right? So if your monomer is electron rich enough, then non-enzymatic oxidation can facilitate dimerization events between two phenol units or naphthol units. And then sometimes there's an unidentified dimerase, if you will, meaning we simply don't know how the dimers arise, right? So these are kind of the four categories, or the four means that you can get dimeric natural products in nature, right? But we were really interested to note that nature doesn't use this building block to make dimers. This what we call beta keto adityl-CoA, right? So you can see it contains a 1,4-dicarbonyl unit here. And interestingly enough, these dimeric natural products that have a hidden 1,4-dicarbonyl unit don't use this as a building block. And so part of the inspiration for these projects going on in our lab were based on this idea. Maybe we could come up with a reagent that functioned as this protected 1,4-dicarbonyl unit so that we can build dimeric natural products. And I think that'll become more clear on the next slide. Okay. Oh, nope, not the next slide, the slide after that. All right, before I get into actually what we're gonna do in the lab, I just want to cover really quickly how some of these dimeric natural products are made traditionally. So work by Shaw and co-workers in 2011 take these really electron-rich hydroxynaphthalene units, and they're able to forge the CC bond formed in, shown in red by using a vanadium catalyst, all right? And so this catalyst serves as an oxidant. Essentially what you do is lose H2, right? So there's a proton here on this carbon, and in the presence of vanadium, you lose H2 and you're able to form a CC bond, right? Noller and co-workers take a similar approach, right? So you're doing another oxidative coupling, removing H2, but now instead of using vanadium, they're using an iron catalyst to do this, all right? But you're starting to see a trend. Normally what you need to do to affect these dimerizations is you take some electron-rich monomeric unit and then some oxidant, and that forges your CC bond, all right? And then Herzon and co-workers in 2011 showed this really elegant way to make a dimeric, the quartz of these dimeric lamavitison natural products. Essentially what he's doing is he's taking these silyl-enol ethers, shown here, right? He's using a manganese 3 reagent, and he's able to, again, do an oxidative coupling of these electron-rich double bonds, all right? So here, we're not losing H2, we're essentially losing 2 electrons to form this CC bond, all right? Now, all of these methods are great, but they all have their own strengths and limitations. And one of the main limitations for these types of couplings, I would argue, is their ability to access things that are heterodimeric, right? And that's where we came in. So when we looked at all of these molecules, we really sat down and we wanted to find really a general approach to access dimeric natural products, okay? And so we were looking for common features that were found throughout all of these polyketide natural products, right? And so what we noticed is if you squint really hard, we can see this 1,4-dioxobutadiene unit that's hidden throughout all of these complex molecules. And so we said, aha, maybe if we actually target this portion of the molecule, we can not only build molecules like viriditoxin, but maybe also lamavitison A and bisisomahanine. So maybe this would be a much more general approach to building complex dimers, all right? And we thought if we were able to actually form these bonds in blue around this unit, and shown in red, that this could be accomplished, that our transformation could be accomplished. And so as I'm sure most of you are thinking right now, this reminds you of a Diels-Alder reaction, which you probably talked about in organic 1 and 2. All right, and so the general bond forming strategy is as follows. You would take some diene, shown on the left, and this kind of odd carbonyl group. So this is known as a ketene, all right? So it's a special type of carbonyl in that the carbon atom is bonded to, it has another double bond to another carbon, okay? But if we could affect this Diels-Alder reaction between some diene and a ketene, then we'd arrive at these cyclohexenones. And you see these cyclohexenones are really the core that's present in all of these natural products. Now, notice in some cases the enone it's hidden a little bit. It's masked as the enol tautomer. So if you tautomerize, you would get the enol here, right? But we thought this would be a general approach to access these dimeric natural products. Okay, and so to obtain the dimers, essentially what we needed to do somehow is to build something that behaved like a dimeric ketene, also known as a bisketene, all right? So this unit in red is essentially a protected bisketene motif. So we scoured the literature for things that were bisketenes, and we found this report by Tidwell and co-workers, and he's kind of been the big player in this in the ketene field for some time. And what he's shown is you can take these cyclobutene diones, and if you just heat them, they undergo a paracyclic ring opening process to give you a bisketene. Now, this is really exciting, but it arguably had its limitations when you're thinking about building complex molecules. This is a pretty reactive functional group, and so to better serve our purposes, our hypothesis was maybe we could go in with some protected version of a ketene, all right, or some protected bisketene unit. So here, shown in the bottom of the slide, are chloroacrylonitrile and cyanovinyl acetate. And these are kind of the prototypical protected ketenes, meaning normally what people will do is they'll functionalize these molecules, say with a Diels-Alder reaction, okay? And then they'll unveil the carbonyl group in a separate step simply by treating these with water, okay? So you get a cyanohydrin and those collapse to give you a carbonyl, okay? So essentially these two molecules behave as masked ketenes, all right? So we wanted to build dimers of these, and so the reason why we were excited about this strategy was several reasons. One, it was, we perceived this to be a very convergent way of building natural products, meaning we could take a bucket of our linchpin reagent, if you will, and some truncated monomer and potentially access these natural products. We also thought it was modular, right? Meaning that if you could somehow do your first Diels-Alder reaction with your first truncated monomer, maybe in a separate step, you could come in with a different truncated monomer to get heterodimers. And that's kind of where we were excited about this methodology. All of the other strategies, you're particularly limited to homodimeric compounds. And then lastly, this was unexplored. The chemistry of bisketenes and their protected versions are not well understood. So to this end, we kind of scoured the literature for what was known about protected ketenes and protected ketene equivalents. And so kind of here on this slide, I have a variety of these molecules that are shown. And when you actually think about how to make the dimeric versions, this is where things kind of break down a little bit, right? So we're already starting with pretty difficult alkenes to build. Now building the protected bisketenes becomes a challenge. So after scouring the literature, we settled on these halogenated mucononitriles. Okay, so these are 1,4-diene nitriles that have halogen groups at the 4 position also, because these were the most synthetically tractable molecules in our opinion. Okay, so to that end, we began these studies by synthesizing these halogenated mucononitriles, and it was known to make these, you could start from these orthophenylene diamines. So these are aromatic molecules with 2 amine groups, and we would need the orthophenylene diamines that contain halogenation at the 1 and 4 positions, okay? And so we had to build this kind of unusual arene that had a 1, 2, 3, 4 substitution pattern, all right? Now we thought, well, maybe this can come back from the orthophenylene diamine, but I'm sure as you all have learned in Organic 1 and Organic 2, the problem with starting with this as a starting material is that if you try to brominate this, your bromination happens para to the nitrogen atom. So we know that these are orthopara directors, and because of sterics, the para position is typically preferred, all right? And then once you brominate the first time, that bromine atom is also an orthopara director, even though it's electron withdrawing. So it directs the other bromine atom here, all right? So that doesn't give you the right functionalization pattern that you need. In fact, this is a known transformation in the literature. So we had to think of some innovative way to get this 1, 2, 3, 4 functionalization pattern for this, all right? And so this project was spearheaded by One of my first graduate students, Adam Zahara, he's a rising third year now, and a postdoc in our lab, Dr. Elsa Hines, who's on the job market at the moment. And this work was ultimately published last year in OrgLet, okay? So what we found is that we could use these kind of unusual heterocycles called benzothiodiazoles, right? Now, we like to take inspiration from all parts of the literature. And one of the things that stuck out to us was that material scientists use this heterocycle quite often to make this brominated version for like OLED applications. All right. And we got excited about this because we noticed like, hey, if you brominate this benzothiodiazole, you actually get this 1, 2, 3, 4 functionalization pattern that you need. Because these nitrogens are now essentially masked as imines, they become they no longer direct to the pair positions, and you can get this ortho-selective bromination. Okay, and so after reducing this heterocycle down, we can unveil the orthophenylene diene. So we use sodium borohydride in combination with cobalt as a catalyst to do this reduction. So this does a desulfurization, remove sulfur. So you get this orthophenylene diene, and then what you do is you treat this with lead tetraacetate. So this is not a reagent you want to use lightly. It's pretty toxic, as you can imagine, but we exercise really strict safety protocols at UNC. And using lead tetraacetate, we can actually break the CC bond in this aromatic ring to give us our halogenated mucononitriles. All right, so we had a 3-step method to make this, and we could do this on gram scale, and it was very reproducible. All right, to get to other halogenated derivatives, we've also made the chlorinated version of our mucononitriles. All right, and to do that now, we just simply switch Br2 for this chlorinating reagent, which is known as dichloro dimethylhydantoin. All right, so this is a special chlorinating reagent, and it was found to be the most optimal in our transformation. And we can again chlorinate at the 4 and 7 positions of this heterocycle, and we follow the same 2 steps: reduction followed by this oxidation to now get bischlorocrylonitrile, which is known as biscan. All right, so we have biscan, and this molecule on top we call in the lab bisban. All right, so we've given shorthand names for all of our reagents, and now we're almost ready to kind of test some of the chemistry of these molecules. But before we do, we actually had to prove that we had the right molecules. All right, and you know, when we started out in this project, we didn't really think twice about this. We were like, yeah, we're just going to go ahead and make biscan and bisban, and this is going to be all great, and we're going to make some natural products and save the world. But we noticed early on a big problem is when you look at this molecule biscan by proton NMR, it's a singlet. It's a singlet, and it's a singlet that shows up at about 7.27. So for those of you that are doing an undergraduate research, you know that's right near chloroform. So when we actually made this molecule, we weren't sure that we actually made it because the singlet of chloroform and the singlet for this molecule are practically overlying with each other. They're directly superimposed with each other, okay? So we turned to carbon NMR to determine whether we actually had this. And what we see is very clearly 3 distinct C13 resonances, okay? So that kind of suggested, hey, we have biscan, right? But we still had to be sure that the geometry of these double bonds was correct, all right? Now, we know we can have either an E olefin or a Z olefin. So if we just swap these 2 groups on both ends, then that would also produce a compound that would give you a singlet by NMR. So how do we know the difference between the EE isomer and the ZZ isomer, all right? The way we did this actually was kind of fun. Normally, when you're looking at C13 spectra, the reason why all the peaks appear as singlets is because we're doing what's called a proton decoupled C13 spectrum. So protons are spin active. This is why you can see them by NMR, and so are carbon atoms, all right? And we know that 2 spin active nuclei should couple to one another, right? But we tell the instrument not to let protons couple to carbon atoms, because if we allowed them to couple, that would usually produce spectra that are too complicated to interpret. So this is why C13 spectra always show up as singlets. It's kind of like a dirty little secret of NMR that you're not, that you don't cover in too much depth in organic 1 and organic 2. You just are kind of told, hey, C13 NMR, you get singlets for everything, and you don't have to worry about coupling, okay? But what we did is we actually turned on the coupling. All right, so we let the protons couple to the C13 nuclei. And what you can see now is that all of our things that were singlets become complex multiplets now. All right, and so this resonance at 112.5 is the resonance that corresponds to the nitrile group. And what we can do is we see it's a complex multiplet, and this arises from actually second order coupling patterns. So this is really advanced NMR spectroscopy at this point. But what we can do is we can actually simulate this multiplet using freeware that's found online to calculate the J values for this second order coupling to between this hydrogen atom and this carbon. All right. When we do that, we find out the J value for the coupling constant for this hydrogen to this carbon atom is about 13, and that is in line with these groups being trans to one another. All right, so we had firm NMR evidence now that we do have a trans relationship and not a cis relationship between the proton and carbon. So we definitely did have bisketene. But just to be sure, we got X-ray crystallographic data too. So we grew a crystal of this compound, which is actually a tan solid, and we were able to use X-ray crystallography to determine its structure. I should mention that my first grad student, Adam, he's a go-getter. He likes to do really hard, difficult things. So he actually took our X-ray course at UNC and taught himself essentially how to collect his own X-ray crystallographic data. All right, so because there wasn't much known about halogenated muconinitriles, we started by just exploring the basic reactivity of these compounds, all right? So we saw these first and foremost as glorified microacceptors, right? So we figured if we take these with a soft nucleophile, such as a malonate, we could do conjugate additions into these molecules, right? And then after forming a carbanion, maybe this would essentially kick out chlorine as a leaving group. So what we're doing is a conjugate addition that is also a substitution reaction. And that worked pretty well, right? And so we were able to take a variety of monosubstituted malonates. We can add them into bis-chlorocrylonitrile or bis-bromocrylonitrile. We can get these dimeric looking molecules and pretty good yields across the board, okay? And so we've done this for a variety of molecules now. And, you know, arguably when we submitted this work, one of the questions was, well, what do you use these molecules for, right? And, you know, I'll be transparent with you. We didn't really have a great response to that because honestly, we were just studying the basic reactivity of these molecules because they had not been discovered. But, you know, upon thinking about this, we really do think we can apply some of these to some complex natural products, as well as we think these types of dimeric motifs might be interesting monomers for various polymerization reactions, all right? And to that end, we did try some conjugate additions with more complex beta keto esters, such as this one derived from an endanone and this tetralone derived one, shown on the bottom of the slide, right? We were able to get double conjugate addition reactions to happen in both of those cases as well, okay? And what was really interesting here is that now we're starting to get to things that look like these complex natural products like the lamivitizins, which I've shown on a previous slide, okay? And when we do these conjugate additions with these beta keto esters, we notice that we obtain really high diastereo selectivity. So notice we're forming two stereocenters in this process, and we exclusively form, or we predominantly form the dimer that is C2 symmetric. So it may be hard to appreciate, but this compound that we formed is actually chiral. And I think this actually brings up some really nice opportunities down the line for doing enantioselective transformations, enantioselective conjugate additions, okay? And so kind of what we learned from these studies with these malonates is that with excess nucleophile, double addition always occurs, all right? So we always see these double addition products. The addition reaction is stereoretentive, meaning we don't isomerize the double bond in this process. And monosubstituted malonates seem to be required, all right? But we're very excited by these results because these double additions really, we thought, set the groundwork for building symmetrical dimeric natural products. And I'll show you what we mean on in a few slides, all right? So we tried other soft nucleophiles such as amines. I won't spend too much time on this slide because, you know, these are kind of working in a similar fashion. So the amine essentially does conjugate addition. We form like a carbanion, and that essentially ejects either a chloride or a bromide ion, all right? And so our products now are these dienamines, all right? And this works extraordinarily well across the board for various heterocyclic amines, such as this morpholine-derived one or this thiomorpholine-derived amine. We can also use these pyrrolidines, as well as some pyrrolidines derived from amino acids, such as the proline. So this is derived from a prolinate ester, right? We can do larger amines such as these azapanes and also these complex bicyclic amines as well. All right, so amines add in quite nicely, and we've done this for a number of substrates for both the bromo and chloroacrylonitriles. And we learned a few things from these studies as well. This time, what was interesting to us is with excess nucleophile, we only observed mono addition in all cases, right? So even with 3 equivalents of our amine, we don't see double addition. And this makes sense because after the first addition, we've created a dienamine, and we know those are nucleophilic. So essentially what we've done is we've deactivated this position here to prevent other nucleophiles from adding in, okay? This addition reaction was also stereoretentive, and we found primary amines also worked, but at a lot lower yield, so we're not ready to talk about that data yet. But these single addition reactions, in our mind, provided us as a route to desymmetrize these systems, okay? So remember back at the beginning of the talk, we said we wanted to access both homodimeric and heterodimeric natural products. And so with our linchpin reagent, we really needed a way not only to access homodimeric motifs, but also heterodimeric motifs as well. All right, so to that end, what we tried to do is we tried to do a mixed reaction, right? So can we add a malonate first and then trap the resulting monoadducts with an amine? And the answer to that is yes. So we can start with bischloro or bisbromoacrylonitrile, react it with this tetralone-derived malonate. And now we're using not excess malonate, but we can be using 1.25 equivalents, all right? So this gives us the malonate mono addition product, which we can't isolate, all right? It's pretty unstable. But what we can do is simply just add amine to the reaction, and in 60% yield over the 1-pot 2-step sequence, we can arrive at these desymmetrized adducts now, okay? And so we played all sorts of games with these substrates, right? We can take the dienamines now. If you try to add a malonate into those, that does not work, but we can form CC bonds other ways, right? So we can do palladium catalyzed cross-coupling reactions to form a CC bond from these from phenylacetylene, okay? So this is a Sonogashira cross-coupling reaction, all right? So we can arrive at these kind of unusual dienamines now. And we can also do these Suzuki-Miura reactions where now using, again, palladium 0 and a boronic acid, we can cross-couple to form a bond to these arenes, okay? And then finally, we wanted to test to see whether we can actually make CC bonds to the internal positions of these molecules, which is going to be important for some natural products. I'll show you on the next slide. So we can take, again, these malonates now, we can take this band and then cap this off with morpholine, all right? And then now treating this whole compound with aluminum trichloride, we can actually affect a Friedel-Crafts reaction with the enamine portion of our molecule, all right? So we can form these CC bonds now in quite an efficient fashion. Okay, so why do we care about this? All right, so we care about this because we're really excited about these molecules, bisisomahanine and bismahanine. These are hydroxycarbazole natural products. So this is a carbazole, and here's the hydroxy group off of it. So they're hydroxycarbazole dimers, and they're both found in nature, but they have really interesting, unique dimerization patterns. So what you notice about bisisomahanine is that it's a symmetrical homodimer, okay? Bismahanine is also a homodimer, but it's non-symmetrical, right? So these unique dimerization patterns, and in addition to their biological activities, so these compounds have moderate antioxidant properties, and bismahanine actually has been shown to have anti-cancer properties as well. So because of this, we were really interested in using our methodology to apply our methodology to the synthesis of these two molecules, right? So we envision these symmetrical homodimers such as bisisomahanine being derived from a malonate, Okay, so we know that taking malonates with our linchpin reagent, they'll add in twice. Okay, and so what we thought we could do is take this truncated monomer, right, add it in twice, and we would have pretty much the entire carbon skeleton we need to build something like this isomahanine, right? And then for these non-symmetrical homodimers, we envision taking our malonate again, adding it into biscan or bisban, and then trapping that adduct with an amine, right? This would allow us to form a CC bond to the internal position, and then maybe we could go back and form the rest of the molecule later. So it allows us to desymmetrize the system now. All right, so how does this work in practice, right? In our laboratory, what we found is we can take gramine, which is extraordinarily cheap, commercially available molecule, right? We can derivatize gramine in a single step, or excuse me, a two-step, one-pot, two-step sequence. So we can essentially substitute this amine group out for malonate and then protect the nitrogen with a Bach group. It's a tert-butyl carbonate group. Okay. And then simply treating this malonate with sodium hydride, we'll deprotonate the most acidic position, and then adding in our linchpin reagent, biscan, we can arrive at this dimeric molecule in 83% yield over n gram scale. Okay, so this takes 3 steps, and we've already gotten most of the carbon atoms we need for our natural products. Okay, so all that really remains is we have to find a way to build CC bonds to the internal positions of these homodimeric species. All right, and one of the important things with planning synthesis synthetic routes is we have to make sure our starting material is scalable, which it is. So Adam can come in on any day and essentially bring up 20 grams if he wants of this indole malonate. All right, and so here's just a picture of that kind of in our laboratory. Right. So again, we can for accessing these non-symmetrical homodimers, we can take this indole malonate now, again react it with bisban and trap with an amine. Now treating this with trifluoroacetic acid, we essentially do another Friedel-Crafts reaction, okay, to form this CC bond to the 2 position of our indole. Okay, so now we have this this tetrahydrocarbazole motif, and all we have to do is again build CC bonds to this aminoacrylonitrile unit, maybe using a Diels-Alder reaction, right, and unveiling the carbonyl groups to arrive at our natural products. All right, so really the remaining challenges here are constructing these CC bonds to the internal positions, cycloaddition reactions across this aminoacrylonitrile unit, and elaborating both of these kind of model systems to the final natural products. All right, and these studies are still ongoing in our lab. All right, but I do want to bring up the point that this is extraordinarily versatile reagent. We can essentially take any of these indole we can make any indole malonate that we want. Just pick your malonate, pick your indole. You can make that monomer essentially in one step, and then adding it into biscan or bisban produces a wide variety of substrates. Now we do have limitations. So phosphonate groups or phosphonoacetate groups are not readily incorporated into these molecules, and tosyl groups seem to give us a problem too. Okay, obviously when you start to get to larger esters, such as these tert-butyl esters, the yield drops significantly because we're a little too crowded around this all carbon quaternary center. Right, but we were excited about this strategy because we now have a way to incorporate a wide variety of molecular diversity, and in addition, we can have different functional handles now to explore ways to build these CC bonds, such as using again palladium catalyzed cross-coupling reactions to do what's called a Heck reaction across this double bond. Okay, so we're trying that. And, kind of just to wrap up this section a little bit, we also looked at these indole malonates containing these allyl groups. And one of the ways we thought about making these CC bonds is by using a paracyclic reaction. So this is kind of an interesting reaction where in the presence of palladium-0, we envisioned deallylating this molecule. And then this carboxylate that we would get would essentially spontaneously lose CO2. Now, in the presence of palladium, what that does is it actually helps to install a double bond here, right? And so we were trying these deallylative oxidative decarboxylation, right? And these are very well precedented by people like Suji, Trost, Tungi, Grinning, Newhouse, Stoltz, and many, many others, right? What we found is something actually pretty interesting. Oh, sorry, here's the proposed mechanism again. So in the presence of palladium-0, we dealylate to form this palladium complex that would lose CO2, and then this would beta hydride eliminate to form a double bond. Okay, what we actually found in our hands is we didn't observe any of the double bond formation, but we formed this tetraalylated product. Now, this doesn't help us get to a natural product, but we thought it was really interesting because we're forming an all-carbon quat center here, and this is an unprecedented reaction. Here's the NMR for that substrate. Okay, so kind of in the last 5 to 10 minutes, I wanted to talk about our this Diels-Alder reaction again. Right, so I kind of alluded to us wanting to do a double Diels-Alder reaction, but I haven't shown you any of those transformations. So I want to mention that this reaction, it's non-trivial, and it took us a while to figure out how to actually get this to work. All right, and so here's the proposed transformation. Essentially, you know, when I presented the problem, essentially what I was suggesting we do is to take a diene with our linchpin reagent, which is also a diene, all right, and do a Diels-Alder reaction. Right now, normally when you think of a Diels-Alder reaction, you think of this taking place between some diene and a dienephile, okay? But here, essentially what we're asking is a cross Diels-Alder between two diene motifs, all right? So that's extraordinarily difficult to do and unprecedented to my knowledge, all right? So there are obviously some challenge here. So sterics is the big one. Right, so you can imagine any diene, once you start functionalizing out here, in order to do a Diels-Alder reaction, you have to now deal with all of the groups around one or both dienes, okay? We also have to control for homodimerization product, okay? So let's say I am able to do a Diels-Alder reaction. How do I stop two of these dienes from reacting with each other, or two of these for that matter? We want exclusively the cross Diels-Alder product. And then last but not least, I'm sure you're all aware that these dienes are conjugated. And so by doing a Diels-Alder reaction across one of the double bonds, we're breaking conjugation, which is pretty unfavorable. Okay. And, you know, we're really taking inspiration from studies kind of from related systems, all right? But again, you know, our proposed double Diels-Alder is very different because we're trying to do it across these two double bonds, which are connected, okay? But what is known is you can do some double Diels-Alder reactions across double bonds that are insulated either by an sp3 hybridized carbon or this, you know, in this case, an sp2 hybridized carbonyl group. All right. So here's some work by Winkler and coworkers in 1994, where again, what they can do is a Diels-Alder reaction between this diene and one part of this divinyl ketone, and then this this part of the molecule is a masked diene. So this will extrude SO2, reveal your diene, and then do another cycloaddition on the other side. But again, notice you have this carbonyl spacer here. So this is a divinyl ketone double Diels-Alder reaction. All right, and one of my favorite examples of you know, a double Diels-Alder reaction is one done by Sidney. This one is different also because now we're not using a diene, we're using what's called a dendroline. All right, so these are kind of unusual, very reactive molecules. But notice it's a diene that's connected essentially to another olefin. All right, so the way these work is actually by doing the first Diels-Alder reaction, we're going to transpose that double bond and put it here. All right, and what that does is it essentially creates a new diene to do another Diels-Alder reaction. Right, so this is a dendroline Diels-Alder reaction. Here's the basic structure for a dendroline, and you're able to build up very molecular complexity very rapidly. Okay. And so Winkler has termed these types of cycloadditions uninterrupted simultaneous and uninterrupted sequential. All right, so, you know, when we set out on this project, we tried these reactions with a variety of dienophiles, and kind of the prototypical one that we like to use for Diels-Alder reactions is cyclopentadiene, right? And what we found is quite nicely, cyclopentadiene reacts really readily with our bis-bromo or bis-chlorochlonitrile to give these mono Diels-Alder adducts. And we obtained both the endo and the exo cycloadducts here, and about 1-to-1 DR, right? But this is really high yielding, and we've done this up to gram scale. And kind of one of the, you know, we were able to confirm the structure of the endo adduct by X-ray crystallographic analysis. Okay. And if we really force the system now, what we can do is we can obtain the double Diels-Alder cycloaddition products, right? Now, this result is not ready for prime time yet. We're still at 55% yield, and we're still trying to characterize the diastereoselectivity for the reaction. So because the endo and the exo products are inseparable, we're not able to fully determine the stereochemistry about these stereocenters. But we do know from mass spectral data and from NMR data that we do have a double Diels-Alder cycloaddition. So that was really exciting to us, and we're currently exploring this for other types of systems now. We're looking at these benzocyclobutanes. So these are obviously really strained molecules, and just simply heating these to 80 degrees, what they'll do is they'll ring open. They'll ring open and de-aromatize this benzene. So this de-aromatized benzene is a really extraordinarily reactive diene, and we can do Diels-Alder cycloaddition reactions now across our biscan or bispan. And now we're starting to get to things that really look like the natural products we want. Okay. And so with bromine and chlorine, we get these yields and these these RRs. So in this case, we actually don't observe diastereomers, we observe regioisomers. So we get a Diels-Alder adduct that takes place to place this nitrile group close to this O-tips and one that places it away. And what we think we're dealing with here, right, is this bulky O-tips group prevents this group from the diene approaches in such a way to place this larger acrylonitrile unit away from this O-tips. And currently what we're doing now too is we're performing quantum chemical calculations with Professor Brandon Haynes at Westmont College out in California to understand the energetics of these Diels-Alder cycloaddition reactions. So we're looking again now at bischloro and bisbromocrylonitrile, and we're calculating the barriers for these types of processes. Okay, so I think I'm 2 minutes over, Desmond, but I think I maybe made it on time. I'd like to give a shout out to the team. All right, so again, we're a new group at UNC, and we got a bunch of exciting projects going on. But I really have to give a shout out to Adam Zahara, who is really the leader on the project, and our postdoc, Dr. Elsa Hines, who's helped us out too. I'd like to thank the rest of my group, our undergraduate student, Andrew Morrow. If you'd like to know more about what we do, check us out on our group website or follow us on Twitter. I'd also like to point out this publication that recently came out last year. This is a collaborative commentary, and I think it's on diversity, equity, and inclusion. And the reason I'm including this here is because it really sums up the philosophy of our research group and how we treat each other and how we do science at UNC. So I know sometimes, like, thinking about going to grad school, it can be pretty intimidating and be faced with a lot of challenges. But if you're kind of curious about my mentoring style and just kind of the environment at UNC and some of these other institutions, please check out this publication that was released last year in ACS Central Science. Okay. So with that, Desmond, thank you so much for the invitation out today, and I would be happy to take any questions.
Very good. Thank you very much. So it sounds like we have a question right off the bat. Aaron Jacobs, one of our seniors. Do you want to unmute and ask a question, Aaron?
All right, there we go. Can you hear me?
Yes.
Okay, sorry. Yeah, I gotta ask quickly, but I have to go to inorganic, so I'll make it fast. So that lead acetate reagent that you were using, do you have any plans to replace that reagent? Because from what I saw, it has some lower yields, and also it's quite toxic, and that could be potentially difficult to scale up if you're trying to make this into a medicinal product, say where you're making kilograms or so.
Yeah,
on the horizon.
Yeah, so Aaron, excellent question. And this is a question we get a lot. It's one of these things where when we set out and designed this synthetic route, we didn't want to use lead, but that's the thing that worked. Unfortunately, we had to beat our molecule with a hammer, so to speak, in order to get to break that CC bond of the arene. Excuse me. To answer your question, yes, we are looking at different, we're looking at alternatives right now. So we're looking at some of these hypervalent iodine reagents that have been pioneered by the Winogrent lab up at Temple in Pennsylvania. And we're also looking at electrochemistry to accomplish some of these transformations as well. So I guess kind of the interesting thing is too, some of these hypervalent iodine compounds such as like sodium periodate have been reported to do this transformation, but in our hands, unfortunately, we haven't been able to reproduce those reports. So we're currently investigating a wide variety of ways to do this, but you're totally right. Lead is much less than ideal. And if anyone in the audience has a good suggestion on how to overcome the use of lead here, we'd be open to taking that suggestion.
Okay, very good. Yeah, that was one of the things that I wanted to ask you. So Aaron and I were thinking along the same lines. Anyone has other questions? So your interest in these dimerics, is that something that you started thinking about when you were doing your postdoc, or sort of when did you become interested, and was there any active research in that field, or is this totally,
Yeah,
yeah.
That's a great question, Desmond. So I'd say this field has been active for some time, right? Like dimeric natural products have been around forever, and people have synthesized them for as long as you can imagine. All right, but my interest primarily is really changing the way we think about making these, right? So like one could argue that's the best way to make them, do a homodimerization, right? And I would be hard pressed to argue against that. I think that's a fantastic way to make some of these molecules, but the fact remains there are still limitations, right? So a lot of these dimerization reactions that people have developed, you can't do enantioselectively selectively. I mean, there's some specific ways you can do this. I think Jared Shaw has maybe some chiral vanadium catalysts or some chiral catalysts that can do some of these enantioselective, oxidative, biaryl or biaryl couplings, but by no means is that general. Now, there are some people out there that are looking at biocatalysis to solve this problem. Okay, so presumably if nature makes these through bioenzymatic ways, then why not just use a chiral enzyme to do these too, like one that's obtained through artificial or directed evolution, right? So that's one possibility, but primarily we were really interested in these from a fundamental standpoint. We're excited about ketenes as functional groups and potentially using this linchpin reagent for other types of transformations. So me personally, I've been thinking about this since grad school. Yeah, I've been working on dimeric natural products since grad school, and I personally didn't make any then, but it's definitely been something that's on my radar because I think there's room for a lot more innovation in this field.
Yeah. Okay, sounds good. It seems like Isabella has a question. Isabella, you could unmute.
Yeah, so my question was, do you have a favorite reaction or product that you think is most promising for future synthesis or treatment when it comes to complex molecules?
Yeah, so Isabella, that's an awesome question. Favorite reaction. Oh boy, that's a tough one because there are so many reactions. I think my favorite reaction, which I didn't talk about today, is probably the Akhmatovitz rearrangement. Okay, so it's kind of a complicated reaction that unfortunately I don't think we'll have time to go into. Do I think it'll help access some natural products? Well, I mean, it's already been used in a number of syntheses. As far as things going on in our lab, kind of another area we're interested in are these like frustrated Lewis acid base pairs. I wouldn't say that's like a particular reaction, but I think that's very they're a unique class of molecules that are displaying really interesting reactivity, okay? And if you're not familiar with these, they're essentially a combination of an acid and a base that normally, you would think of those as neutralizing each other, but they're too big to do that. They sterically can't neutralize each other. So we're looking at some of these molecules to, these frustrated Lewis acid base pairs as ways to, couple two molecules together or build cyclopropanes or do other things that nature does really well that we can't normally do in the flask. Does that answer your question? I feel like I was all over the place.
Yeah, that's really interesting.
Okay. Yeah, I think that you call it BISCAN.
Yep.
I like that because it, in a way, one of the things I think about organic synthesis is to try and use small molecules, and your BISCAN is indeed a small molecule that has functional groups, multiple functional groups within that small molecule. Because there's, you know, when you have that type of um, when you have that type of system, I think you start to get unexpected reactivity. Um, and exploring, you know, even though there are some limitations in making it, I think looking at all of the different types of reactivities that it has and being able to functionalize it in a stepwise way, or, you know, all of those sort of things, that sort of fundamental
Mhm.
chemistry of small, what I call densely functionalized small molecules,
Right.
really.
You're absolutely right there. So one of the reasons we're going after these halogenated muconinitriles actually stems from some of my grad work where we had one of these densely functionalized molecules. It was also a dinitrile, but we had acetates where we have the halogens now.
Okay.
And what we found is actually those don't do Diels-Alder reactions. They will essentially cyclize on themselves to give you an oxidopyrrolium ion, and those will do 5+2 cycloaddition reactions.
Okay.
So that we thought that was really cool, but we totally agree with that philosophy, Desmond. I like making densely functionalized molecules, things that are extraordinarily strained, things that have a bunch of potential energy that are kind of like latent, ready to go, because you do find some really neat reactivity that way.
That's right. That's right. Okay. So in terms of other dimeric molecules that are out there, have some of them been in use or being considered, you know, in the late stage of pharmaceuticals or?
Yeah, so what I'll say is this, I've heard rumors that Pfizer was interested in lamivudine, primarily because of its anti-cancer activities. I don't know if this is true. I've never actually talked with anyone about at Pfizer about this. It's just things you hear talking to people. But, I guess the interesting thing about that molecule is literally yesterday, or maybe 2 days ago now, Seth Herzon at Yale recently disclosed that the structure of that molecule is wrong.
Oh.
They actually published studies to show that they published a structural revision of lamivudine. So yeah, I actually have to update my slides now because I can't use that one as a potential dimeric natural product. It's still a dimer, but it doesn't map onto our methodology very well anymore. So we can't use that as justification, but it's still exciting nonetheless.
Exactly.
Yeah.
Okay. So it has the potential for being a monomer for polymerization. Have you guys started to explore that?
Yeah, well, so we've talked about it, but we actually haven't tried it. Like, I think even these 2,2,1 bicycles here, these norbornenes, would be really interesting just to do ring opening metathesis polymerization.
That's true. Yeah, ring opening. Yeah.
So we haven't personally tried this in our lab, but we are talking to people like, oh gosh, why am I blanking on the name? Sorry, we're talking to, Will Gutenkeis down at Georgia Tech.
Okay.
And we're also talking to like Frank Lee-Farth and Alex Zhukovsky in our department too about maybe polymerizing some of these and just finding materials with interesting properties. So we personally, again, to answer your question, we haven't done it in our lab, but we're talking to a bunch of people about it to figure out the best way to go with some of these. But we do have like one polymer project going on in the laboratory that it's nowhere near ready for prime time yet, but I think it'll be interesting.
Yeah, because I'm thinking, for example, if you take this biscan or this bromo and it's, do react it with some sort of malonate, right?
Right.
You react in two difunctional groups and see what type of polymer chain you could get out of that. And now you would have a polymer chain that you could functionalize further because you would have these handles here, the double
Yeah.
bonds and stuff. So
Yeah,
that's kind of what
absolutely.
I was thinking.
That's a great idea. We should try that.
Yeah, I mean, and there to get to some bismalonates sounds like it might be an easy thing or might be something already out there.
Mhm. Yeah, I agree. I think that's a great idea. We should try it. I don't think the bismalonates would be terribly difficult, even if you took something that was derived from like, I don't know, terephthalic acid or something like that.
Right.
Something easy to get your hands on.
Yeah, yeah.
Yeah.
That'll make some interesting materials.
Mm-hmm.
Yeah. Okay. Anybody else has other questions? I know this is more synthesis than probably some of you, but it's okay.
I'm sorry, that happens every time.
It's okay.
David's giving me a thumbs up.
That's all right. Yes. Okay.
And I'm a PChemmer, so it's all good. We want to hear this.
Okay.
I love the NMR decoupling.
Oh, thank you. Thank you.
Yeah, that was interesting too. Really interesting. That molecule had
Coupled NMR.
Yeah,
right. That one peak right on the chloroform peak.
Yeah, that was one of those things as an assistant professor, maybe like 1-2 weeks into your job. I felt like that was our first test.
I know, right?
How do we figure this one out?
Yep. Okay. So if there are no more questions, we want to go ahead and thank you very much. And I know you're assistant professor now. So in a couple of years, we'll check back with you and see what progress you're making.
Okay, yeah, sounds good.
All right. Okay, again, thanks for accepting our invitation.
Yeah, thank you, Desmond. I appreciate it. And everyone take care.
Okay then, take care.
You
Bye-bye.
too.
All right. Okay, very nice. Take care.
See you.
Bye. All right.
Bye.
Bye.
How did